So we have a little equipment shortage, so there's going to be some dead time while we're waiting for the equipment to clear up. We can only do one at a time, one filtration at a time. And so I was thinking during that dead time, what we can do is, if you didn't quite finish the procedure for last week's lab, I'm going to have the equipment available for checkout, so you can get more practice pipetting or buretting or medicine dropping. The medicine dropper one's pretty fast, but you could do that. If you're already finished with that, we'll have you do something else. I have another thing I'd like you to work on as well. So I'll talk about that as the lab progresses. We'll see how fast the filtrations go. Okay, any other questions? What you turn in is just the report sheet. Yeah, the physical paper. Do you have it on an electronic copy of it, or you could turn it in on loose leaf paper. It doesn't have to be the report sheet. You could just write it. A lot of people just hand write it. You know, that's one. But yeah, you need to turn something in for that. Now the labs, in the past, I've taken off a penalty, but in this case, I'm not going to accept late labs. You just turn in what you have. And so this lab, okay, you forgot it or something, but for future labs, if you don't finish it, just turn in what you have. You know, otherwise it becomes complicated grading them. And so I just want to keep things simple this semester. Just collect them all in one day, and then I don't collect them on different days. And so typically the labs are going to be due a week after we complete the experiment, except for the formal reports. This lab is going to be a formal report, and so this one we're going to have a lot more time to complete, and I'll talk about what's involved in the formal report for this lab. So just so you complete the calculations, if you have any questions on the calculations, were there any questions on the calculations for the measurement lab? No? Okay, we can go through those now. So I was thinking what to do, because I know a lot of people don't have this, and there's only one copy in the bookstore. Did anybody pick up that copy in the bookstore? It's for the 11th edition. You got it? Okay. Well, what I decided to do is I was going to put this on reserve in the library, but I thought I'll just make it available in lab. So if you want to take a look at it in lab, you're welcome to do that. Or you could look at it during office hours, if you'd like. If you want to return yours, you're free to do that. But it's pretty helpful to have, I think. Yeah, and then they have advanced problems here, but some of the problems are missing. Even though it says the complete solutions manual, there are a number of problems that are left out. And then some of them, unfortunately, there's a lot of problems, and so some of them have mistakes. So you be aware of that. So if you're getting a different answer or the solution looks a little weird, it could be that the solutions guide's incorrect. I found they try to update it, because this is from the 11th edition. The 11th edition might have a different numbering, but the problems are the same. So you'll have to look around for what problem it is. But I found a number of mistakes that pop up, but a few of them are fairly obvious. All right, so I'll have that available. And then, did somebody lose these from lab? No. I think I asked that before, and so maybe it's not this class. All right, so the first thing we're going to do when we come into lab is we're going to see if we were successful. The whole purpose of adding the barium is to capture all the sulfate, and we want to see, were we successful in capturing all the sulfate? And so how could we test if we were successful in capturing all the sulfate? Well, hopefully your precipitate is now nicely coagulated at the bottom of the beaker. So you should have a layer of precipitate. Yes. And up here we have what's called a CCS. Have you heard the acronym CCS? What does it stand for? Anybody?
Clear colorless solution.
Clear colorless solution. And so here you should have a clear colorless solution. It's not pure water. Is it pure water? No. This clear colorless solution is, I guess, contaminated. Not really contaminated. I mean, we expect it. This clear colorless solution has what in it? It's going to have some cations, which we don't know, except we do know that they can't be a certain, which ones? They can't be certain ones. So for example, there are cations in there because we can't have an anion without a cation, but we know we can eliminate a number of cations. Do you know which cations we can eliminate? Silver, lead, mercury. Is that it? Yeah, silver, lead, mercury. Calcium, strontium, barium. Good. Did you learn those in intro chem, Chem 4? Or
I think it's mentioned.
Or did you just learn those over the weekend?
You went over
Dylan, or do you remember those too?
went over it in class.
Okay. Yeah, I went over it in class last week, but I'm just curious how many people remember it from class last week. Because like I said, I read those studying books, and your memory memory falls off exponentially. It just rapidly decays. So if this is your memory, this is hours. And so, speaking of memory, I bought this class from the world record holder in memory. But some of the stuff, he was talking about, he memorized all the numbers and elements in the periodic table and the names. I thought that wasn't very effective, because if you know the number, like element number 100, what could you tell me about it? He didn't know any patterns. He just knew. If you asked him what element 110 was, he could figure it out. But still, he had some good tips. One of the tips is you got to review. When you first learn the material, you got to review more frequently to bounce this back up. Or not to let it decay. Actually, you learn more frequently. You don't let it decay like this by reviewing it. Otherwise, it just decays like this. And then you can increase the time between reviewing. But if you're in the class, you might as well review it every day. But did I tell you? I told some of you about my friend, my pre-med friend. Did I tell you? Do you guys remember? When I was at UCLA, I was a chem major. He's a bio major, and he was about to take the MCAT. So he asked me to help him review chemistry for the MCAT. And so I said, sure, I can help you. And then when I sat down with him, he forgot everything. Everything. And it turned out, no, you can't take the MCAT on your planned date because you just don't remember anything, And so, I had to give up, because it was just like having to teach him, back from like intro to, it would take too long, basically. And so he ended up taking multiple gap years to review everything, because he just forgot everything. And he eventually made it into medical school, though. I think he eventually made it into the American Medical School in the Caribbean, which is, I heard, is very rigorous school. But That's where he went. I lost touch with him, but anyway. So even after you finish the class, let's say you're preparing to take the MCAT or whatever test, DAT, the dental test or something like that, then you want to like review it like once in a while, like every month maybe. Otherwise, you might end up like my friend who had to take. He took I think 3 years, gap years. He didn't. Number one, his grades weren't that great, so he didn't learn it very well when he first had it, And then what little he did learn, he forgot. So we don't know what cations there are, but there are going to be some cations there. And the other tricky thing is that, these could still be present, but they could be present in low concentration. Although, if they're present in low concentration, then you'd see specks of precipitate or crystals not dissolve. Did everybody get their crystals dissolved? Pretty much without trouble? Okay, then most likely we didn't have these. But I'll put a little asterisk there. Because to be visible to the naked eye, do you know how big a precipitate crystal has to be? You might be able to see, the crystal might not dissolve because it's microscopic. We can't see it. You can't see down to the ion, the actual atom, can you? And so there could be tiny crystals floating around that are just invisible to the naked eye. And so that's an interesting question. That's actually one of the homework problems, so you'll see it in the future, how big a crystal has to be, to see it. And there could be other anions. That like other anions here. Some of these other anions could be potential interferences. And so we'll say including potential interfering cations. Let me know if you can't read this. Uh-huh. Okay, the record? Yeah, I got it. Thanks for reminding me, though, because sometimes I forget to record. And so let's talk about interfering anions, not interfering cations. I shouldn't say that. Other anions, including potentially interfering anions. So we know that barium likes sulfate. And we get a nice white precipitate of barium sulfate solid. PPT is the abbreviation for precipitate. But does barium like any other anions? Yes, it does. What other anions does barium like? For example, does barium like hydroxide? Actually, not enough to precipitate, because barium hydroxide is what we call a soluble hydroxides. Most hydroxides are insoluble, but barium hydroxide is soluble. All hydroxides are insoluble except for which ones? Ammonium, group 1, and calcium, strontium, barium. So barium hydroxide. So hydroxide is not one of those ones that will automatically precipitate with barium ions. Give me one that will automatically precipitate with barium. Phosphate. What's the formula for phosphate? So if you look at the periodic table, phosphorus is in the 4 oxygen or the 3 oxygen group? the 4 oxygen group. So we know it's PO4. And the charge we get from, we know that silicate is 4 oxygen with what charge? 4 minus. And therefore phosphate must be what charge? 3 minus. See, you'll never get the formula for phosphate wrong if you know the pattern. Right? What's the correct formula for barium phosphate? How many bariums do I need and how many phosphates do I need to balance out the charge? 3 bariums and 2 phosphates. Is that correct? It looks like I have 42 oxygens. Is that correct? No, I need parentheses around these. So the rule for parentheses is avoid using parentheses unless you have to. If you have to, avoid using, I mean, if you have to use the parentheses, then use it. Otherwise, you will have confusion. And so we'll have barium phosphate. You know what color barium phosphate is? White. It's a white precipitate. How can we tell the difference between barium sulfate white precipitate and barium phosphate white precipitate? Visually you can't. They look the same. I mean, we could do this. We could try to melt this stuff and see, you know, maybe some melts at a lower temperature, some melts at a higher temperature. That could happen. Or other things to try to do. But that's what we call an interfering anion. So if there's phosphate present in our unknown, then the precipitate might not be barium sulfate. The precipitate could be barium phosphate or a mixture of barium phosphate and barium sulfate. But there are more. There are 2 more interfering anions. What are they? Carbonate. I leave off aqueous. You know, normally I'd write aqueous, 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 aqueous. But if there's nothing written here, that means it's aqueous. What's the formula for barium carbonate? How many bariums? How many carbonates? 1 of each. Do I need parentheses here? No. Do you know what color barium carbonate is? It's a white precipitate. We'll do one more. What else? Chromate. Do you know what color barium chromate is? It's not white. It's a pretty bright yellow precipitate. Did you have any yellow PPT? It's pretty much white. Probably don't have any chromate. Unless it's there in trace amounts, you know, that could be possible. But we're going to take advantage of some chemical properties. What we're going to do is we're going to dissolve the 3 interfering precipitates and leave this one there. And so what we're going to do is we're going to do a, you know, double. Do you guys remember the double replacement reactions? Yeah, sometimes the double replacement reactions don't fit a certain pattern because double replacement reactions have the AB plus CD pattern, which is fine, but sometimes we don't write it like that because sometimes I'll do it by ionic equations. This is an ionic equation or a net ionic equation here. But essentially this is a double replacement reaction because we're taking barium chloride, and I don't know what the cation here, it might be sodium sulfate, might be potassium, you know, some soluble sulfate. The soluble sulfate would be all the cations other than these ones we listed here. And so what we're going to do here is we're going to eliminate the interfering ones and leave this. And this is the purpose of the acid. So if I take barium sulfate solid and I add HCl to this, what should form? Sulfuric acid and? Yeah. And what's the formula for sulfuric acid? Now, what we want to do here before we go on is we want to see if there's a driving force. So I'm not going to balance this. In fact, I didn't balance this one here. This one would be 3 bariums and 2 phosphates. But here, what is the driving force for double replacement reactions? Stronger acid to weaker acid. That's one of the driving forces. Have you heard that one? So what we do is we look for a driving force. For double replacement, but not everything fits the double replacement, so I'm going to call these metathesis. So for example, when I look at the net ion equation, does it look like a double replacement? No, but it is. But instead of calling it double replacement, I call it metathesis. Metathesis, what that is like favorable ion combinations. And so metathesis reaction, you're looking for ions that like one another. And so I'm going to call this favorable ion combinations. A strong acid is strong because what? A strong acid is strong because I'm sorry, a lot of combinations?
Yeah,
Attractions? Yeah, it's more reactive. A strong acid is a strong acid because it's more reactive. And why is it more reactive? Can somebody remind or tell me why a strong acid is more reactive than a weak acid? Well, what else do you know? Tell me a physical property of a strong acid that you might recall. Like, for example, electrolyte property. What is an electrolyte property of a strong acid? It's a strong electrolyte. And what does a strong electrolyte mean? It completely dissociates. So a strong acid is strong because it completely dissociates the H plus cation. And the H plus cation can go on to react with bases. Whereas a weak acid is weak because it only partially dissociates. So that means the anion and the cation are kind of stuck together still. And so therefore the cation can't go off to react as easily. Does that make sense? Uh-huh.
Well, what makes like the H plus or like the thing that the H is connected to, what makes it like leave like the
Leave easier?
Yeah,
So what we do is we try to relate that to what?
charge size?
Well, we do properties are related to structure, and so we have to look at it structurally and compositionally, and then we can see why. And so that involves a number of things structurally. But since we haven't gotten to Lewis structures yet, I'm going to wait on talking about that. But there are 4 factors that we look at when assessing how strong an acid is. And those 4 factors I'd rather not get into now because it takes too much time. Okay. That's for a Bronsted acid. For Lewis acid, it's more complicated. So a strong acid is strong because the H plus can break off easily. And so that's not a great ion combination. And so going from a stronger acid where the H plus breaks off easily and separates from the anion, so the cation and the anion separate, versus a weak acid where the cation and the anion are more strongly attached to one another means that that's a more favorable ion combination. A more favorable ion combination would be a weak acid. And so going from a stronger acid to weaker acid is going from a less favorable ion combination to a more favorable ion combination. But the situation here is this. What is HCl? Is that a strong acid or weak acid? That's a strong acid, so the H plus breaks off pretty much completely. Strong electrolytes have 100% dissociation. What about H2SO4? That's also a strong acid. So we're going from a strong acid to a strong acid. Is that a favorable ion combination? No. And so this is not a driving force. Strong acid to strong acid is not a driving force. We need to go from a stronger, it doesn't have to be strong, it just has to be stronger to weaker acid. And so we'll just put this is in no particular order, but we want to go from stronger acid to weaker acid. And so, for example, strong to strong is not, or weak to strong is not. But how about weak to weak? Weak to weak, yes, it could be, because it depends on how weak it is. You know, weaker acids have a whole, like, it's not black and white, strong or weak. Weaker acids have a whole spectrum. You know, it would be like a grayscale or color. You know, you'd see a whole spectrum of grays. And so some weaker acids are borderline strong. Some weaker acids are terribly weak. And so we have a whole spectrum. So weak to weak could be. Depends on how weak to how weak. We'll talk more about that later. What's another favorable ion combination? Or what's another driving force for double replacement reactions? Gas formation. That's another one. Do these sound familiar? I mean, is this all kind of review? Pretty much. What things form gases? What ion combinations form gases?
Like carbonate in water?
Yeah. Carbonate not in water, but in acid. Probably the biggest one is this. It's carbonic acid. So if you take acid, H plus, acid is always H plus. Actually, let me reverse that. Acid is not always H plus. What type of acids are always H plus? Bronsted acids are H plus. Arrhenius acids are H plus. Lewis acids aren't necessarily H plus. Lewis acids, as I said, are more complicated. That's probably why they aren't covered in much detail in Chem 4 or high school. So when we have carbonic acid, that's inherently unstable and immediately decomposes into what? H2O liquid and CO2 gas. Good. Give me another one. We don't call it hydrosulfuric acid. Hydrosulfuric acid, oh yeah, okay, I know what you're saying. That's good. Hydrosulfuric acid, if we form this, hydrosulfuric acid isn't very soluble in water. And so if you produce hydrosulfuric acid, most of it bubbles out. The solubility of hydrosulfuric acid is only 0.1 molar. And so if we form this, you're going to smell rotten eggs. You're going to smell rotten eggs because the H2S gas is going to leak out of the solution. So hydrogen ions and sulfide ions are a good ion combination. That's going to do it. So hydrosulfuric acid. We call the one on the left hydrosulfuric acid, and the one on the right is called hydrogen sulfide. This has just historically been done. You know, if we followed the rules, then the one on the right should be called dihydrogen monosulfide, but we don't call it that. This is the rotten egg gas, which is quite toxic. Did you know that hydrogen sulfide can be detected at the part per billion level? Our noses are that sensitive. We can start smelling H2S at the part per billion level. So if you smell rotten egg gas, what you'll be able to do is detect it at a very low level. However, what happens is it saturates the detector sites in your nose, or or something. It saturates or fatigues them, and so what happens is you smell it initially, and then your nose is fatigued, and you don't smell it anymore. So you might think the danger has passed because you stopped smelling it, but the danger's still there. It's just you can't smell it anymore. It's been saturated, and that leads to deaths because you can die at the part per billion level for hydrogen sulfide. Okay, what else? Is a gas former. Yeah, hydrocyanic acid would probably be one too. Because HCN, even though we have it aqueous, this would be hydrocyanic acid, it could bubble out to form hydrogen cyanide gas. Hydrogen cyanide gas. So these, even though these are molecular compounds, the acids we kind of name like ionic compounds in the gaseous form. And this would be hydrocyanic. In the aqueous form, we'll just name them as regular acids. Both of these two are very toxic. If you smell burnt almonds, be wary. And in fact, you know how they form this in the gas chamber? They form this by taking a cyanide salt, like sodium cyanide, and adding acid to it. And so if you take a cyanide salt, add acid, you're going to make hydrogen cyanide gas. The same thing. And so we never mix cyanide salts with acid, never mix sulfite salts with acid unless you do it in the hood. That way you aren't going to die or kill by accident. Cyanide, it's pretty much death by asphyxiation. It's like the same thing with carbon monoxide. Cyanide and carbon monoxide are excellent what we call Lewis bases. And hemoglobin in blood is Lewis acid. And so those are non-traditional non-traditional in the sense that they're not your typical hydrogen-containing or hydrogen-accepting acid and base. But they are acid-base reactions, so yes. Give me another one. Ashley, you're on a roll, so. Sulfurous acid. Sulfurous acid is like carbonic acid. It's unstable, and it decomposes into what? It's kind of like carbonic acid. When you look at carbonic acid and sulfurous acid, they're kind of similar. What do you think sulfurous acid decomposes into?
Would it be SO2?
Yes. Right. And what do we call SO2? Sulfur dioxide. Sulfur dioxide If you ever smell the stuff, it's choking. You feel like you can't breathe. Sulfur dioxide is also poisonous, and so you want to avoid it. Sulfur dioxide is when you burn, when you completely combust sulfur. Is this maxed out? What is the oxidation state of sulfur here? Elemental sulfur, like yellow sulfur, is 0, but this is not. This is what? What's the oxidation state on sulfur here?
Is it 4 plus?
It's not 2 plus.
4 plus?
It's 4 plus. That's correct. Good. This is 4 plus. Is that maxed out? No, what is maxed out on sulfur? Look at the periodic table and tell me what. That periodic table is not that great. You want the periodic table with the Roman numerals because the Roman numerals are what it is when it's maxed out. Do you know what Roman numeral sulfur would be? So what you need to do is you need to cross-correlate the Roman numerals with this new system here. What is sulfur? We call it the valence. What is the valence of sulfur? Not 7. 6, yeah, plus 6. Plus 6 is maxed out, but when you burn sulfur, it's hard to get it plus 6. So you might think you'd form a higher oxide, like SO3, but when you initially burn sulfur-containing compounds, it usually burns to SO2. Eventually it could be converted to SO3, but initially what forms is SO2. Though SO2, you'll see it again in combustion analysis. When we do combustion analysis of a sulfur-containing organic, we're going to form water, CO2, and if the organic contains sulfur, we'll form water, CO2, and SO2. In other words, we're going to form oxides. Nitrogen's more complex. If you burn nitrogen-containing organics, you form a range. Nitrous oxide, nitric oxide, nitrogen dioxide, a whole bunch of what we call NOx. And so you'll form a mixture of different oxides of nitrogen, depending. It doesn't burn so clean. So nitrogen is more complicated, and all those are toxic. Except maybe, no, I shouldn't say all those are toxic. All those would be toxic at high, but some of these you might know, like NO1 half. NO1 half is called N2O. N2O is nitrous oxide or laughing gas, so I don't know how toxic that is. If you burn nitrogen-containing organics and it'll only form laughing gas, then that would be probably better than all the other stuff like it could potentially form. Give me one more. Ammonium hydroxide. Ammonium hydroxide is unstable and decomposes into what? Ammonia and water. The difference is the difference is in terms of solubility. Like SO2 is somewhat polar, so it's got a slightly decent solubility, but a lot of it will bubble out. Ammonia's a gas also. And so some ammonia gas will come out, but most of the ammonia stays in water because it's very polar and it can hydrogen bond to water, so it's very much like dissolves like. And so a lot of the ammonia stays as aqueous. A little bit will come out as a gas. If you heat this up, it's a little bit better. So these other ones will show some vigorous effervescence, but this one probably won't show much effervescence, And so a little bit will bubble out as ammonia gas. Okay, that's number 2. What's the third driving force for double replacement reactions? Precipitate. We'll call it precipitation. And this is just formation of an insoluble solid. And so in order to determine if there's a precipitation that's going to form, we need to look at the solubility rules. Or we need to go to the CRC Handbook of Chemistry and Physics. What else? The MSDS, sometimes it has physical data like that, sometimes not. The CRC, give me the big 2. The CRC is one, and the other one is drug company, Europe. The Merck index, or Wikipedia. My friend asked for help with the MCAT, which is like the medical entrance exam. He wasn't a very serious student, but other of my friends were extremely serious. I mean, it was their dream to go to medical school since they were like kindergartners. And the amount of study they did was like, the only thing they focused on was, doing that. So you gotta realize that, you gotta, and UCLA is a very popular pre-med school, and so you're gonna be competing against people who've already started preparing well in advance of the quarter. Those people are on it. So when the first day came, they were already ahead of the rest of the class. Everybody else was behind if you started studying on the first day class. They were studying well before. And they ended up going to maybe more. Well, anyway, just think about that, because it's a much more competitive environment, and so you'll want to stay on top of it, the material, as best you can. It also depends on how much free time you have and those types of issues. And so, is H2SO4 a weaker acid? No, we already eliminated that. Is H2SO4, does it decompose into gas? No. H2SO3 does, but not H2SO4. Does H2SO4 precipitate? No. Okay, how about barium chloride? Is barium chloride a gas? No. It's not an acid, at least a Bronsted acid. And the final thing we ask is, will it precipitate? No. Chlorides, bromides, and iodides are all soluble except for silver, mercury, and lead. And so this is NR, no reaction. And so this is why they were, they gave me a cocktail of barium sulfate. I actually ate this stuff. Well, I drank it. It tasted like chalk, paste. Chalk paste. And it tasted, I shouldn't say it tasted awful, just the texture was awful. It's like eating chalk, which doesn't taste bad, but it's all right. But at least I know that when it hits your stomach acid is a hydrochloric and butyric acid. When it hits your stomach acid, are you going to worry about it dissolving and the barium ion attacking other things that it shouldn't attack instead of, let's say, magnesium and calcium? Because you don't want barium to start competing with magnesium and calcium, do you? Not necessarily, because it could change your biochemistry. And so this is good. It's good that there's no reaction. That's good. So I didn't even bother balancing it. We don't have to balance it because there's no reaction. But this is only metathesis. You know how many different types of chemical reactions there are? Well, if you think about the human body, how many different kinds of chemical reactions occur in your body every day?
A lot.
A lot. You know, but are there any patterns to it, or do you have to study them one by one? Say they're trillion or billion or thousand? You know, how many chemical, and are all those chemical reactions well sorted out? Or, you know, do they know everything inside a cell? You know, could there be trace things that are hard to detect that they know are maybe in there because of the reactions that occur, but maybe they don't know? Do they know every single molecule inside the cell? Do they know, like, for example, you know, there's some stuff, there's like there was a lot of speculative stuff that was happening recently, you know, about, especially like about, you know, a lot of vaccines are very effective, but, you know, when somebody claims they know, like, it's 100% safe, is it really 100% safe? Do they know every single interaction, every single chemical reaction that occurs in the body and how that could be impacted by certain things? You know, if so, then yeah. But, you know, there's of course there's a certain limit. You can't, you know, in order to know everything, you'd have to live like an infinite amount of time or something. We don't know everything, so we got to do the best we do with the observations that we have. And so if it appears safe, then you can say it appears safe. But you know, to say one like a declarative statement that it's 100%, then you, I think, are like outside of science. But anyway, let's go here. So we have no reaction for metathesis, but there are other types of reactions. And all the other types of reactions, let's say in your body, a lot of these other types of reactions we can think of, or maybe not in the body, but for inorganic, because we can subdivide them into many, many different categories. But if we subdivide these reactions into three broad categories, then we think about others. The other types of reactions would be potential acid-base reactions that might occur. And I said Lewis acid-base are a bit more tricky, and so you have to look more deeply at that. For example, cyanide is a Lewis acid-base reaction with hemoglobin, and hemoglobin's the Lewis acid. And so we have acid-base, we have redox. And so this is no reaction for metathesis. And it turns out there's no reaction for acid-base and no reaction for redox, but we'd analyze this to make sure. However, for barium phosphate, let's take a look at what happens with HCl. With HCl, what forms? Phosphoric acid. What's the formula for phosphoric acid? H3PO4 plus barium chloride, BaCl2. Okay, we already know barium chloride is not a driving force, but all we need is one driving force, and this reaction can occur. And then we know that HCl is a strong acid. What about H3PO4? Is it H3PO4 one of the 7 common strong acids that you memorized? No. And so there is a driving force here. So what we're going to do is I'm going to go ahead and balance this in a minute, but we're going to say we're going from a stronger acid, SA, to a weaker acid, WA. So this just stands for stronger acid to weaker acid. That would be the driving force. Help me balance this. And the way we balance this is we don't balance metathesis reactions usually by atom. We balance it by ion. So how many barium ions do I have over here? 3. How many do I have over here? 1. So I'm going to put a coefficient of 3. That gives me 3 bariums on each side. How many phosphates do I have? 1. So the phosphates are balanced. How many H's? I screwed this up, sorry. Barium phosphate is Ba3PO4 2. So how many phosphates do I have? I have 2 phosphates on the left, and so I'll need to put a coefficient 2 here. And that's going to give me how many HCl's? 6. So when I look at this, I'm taking a solid and an aqueous solution, and phosphoric acid is not a precipitate. It's going to be aqueous, and barium chloride is also aqueous. And so what I do is I dissolve the precipitate. And so I have a driving force, and I'm going to dissolve my precipitate. And so this is removing barium phosphate as a potential interfering anion. Okay, next we'll go to barium chromate. Or no, let's go to barium carbonate, sorry. If I go to barium carbonate plus HCl, what forms? Carbonic acid. What's the formula for carbonic acid? H2CO3 and barium chloride. So one thing about carbonic acid is we know it's unstable. So I'm going to put it in quotation marks here. I'm going to put it in quotation marks here because I need to decompose this. This decomposes into what? Water and carbon dioxide. This is an example of a Lewis acid-based decomposition. You have this Lewis acid base. In fact, water is what we call a Lewis base. The water can go both ways. It could be an acid or a base. But CO2, did you know CO2 is an acid? Is CO2 one of the acids on our chart? No. CO2 is what we call a Lewis acid. So, like if you hyperventilate or other things, that can change your blood pH. One of the ways we maintain our blood pH is by exhaling CO2. CO2 is an acid. Otherwise, the pH goes too low. It becomes too acidic. And we have something called acidosis. So anyway, this is a Lewis acid-based decomposition. We'll talk more about that later. Now let's look for a driving force. Now the driving forces are going to be a bit easier here because the driving force is going to be gas formation. And we have 2 here. The other driving force is going from a SA to a WA. Carbonic acid is a weaker acid. CO2 is a weaker acid. And so you could say either SA from HCl to carbonic acid, or you could say SA from HCl to CO2. CO2 gas is a weaker acid. But it's what we call, again, a Lewis acid, not a Bronsted. And it's not going to be on the chart. On the chart that you're going to see, that we're going to use, the acid strength chart, is going to have HCl and carbonic acid. Let's balance this. This one's a lot easier to balance. What do I need here? Well, what I do is I balance by ion. So this is one of the reasons why I leave carbonic acid in there is to balance it, but I immediately decompose it. Because if you don't decompose it, then we're not going to actually be able to capture carbonic acid. We're only going to be able to capture this stuff. And so I have one barium, one carbonate, one H. I have 2 H's, so I'm going to go 2 HCl's here. 2 chlorides. Now it's balanced. And so we have 2 driving forces for this particular reaction, and that's going to eliminate formation of barium carbonate interfering with this. And finally, we're going to have this one. It's going to be barium chromate, solid. We already know this one we don't have anyway. But what is this going to form? Chromic acid. What's the formula for chromic acid? H2CrO4. Let me speed it up because I don't want to take too much time. talking about this. So here, the driving force is stronger acid to weaker acid. Chromic acid is not one of the 7 common strong acids that you memorize, so this one we don't even need to look at the chart. If we're going from weak acid to weak acid, we have to consult the chart. There's an acid strength chart. Have you seen that before? We would look at that if we're going weak to weak. But now we're going strong to weak, no problem. And so what this is going to do is it's going to dissolve. And so all these precipitates will dissolve except for barium sulfate, and that's going to eliminate any interfering anions that we may have. Okay, so what we expect to have formed, that precipitate should be pure. The precipitate that we form should be pure barium sulfate on the bottom. But it's not pure. Well, it is pure if you just look at the precipitate, but it's not pure because it's sitting in a solution containing a whole bunch of other stuff. And so when I look at the CCS, that's what makes it impure. What makes it impure is the solution above this I do. It's like, okay, let's say you want to take a bath. You go take a bath in the ocean. Do you feel clean afterwards? No, you feel salty, right? There's a whole bunch of salt on your skin. And so what do you need to do? Usually when people go swimming in the ocean, the first thing they do when they come out is to wash off, you know, either with a shower, maybe there's a shower at the beach, you just wash off all the ocean water, right? Well, the same thing, this barium sulfate is going to be like in this salty solution here. And so how are we going to wash off the barium sulfate, you know, because this is going to feel salty. And so the way we're going to do that is this. We're going to filter it, but the filtering process for small crystals is we need very fine filter paper. But very fine filter paper is too slow to filter. So what we're going to do is we're going to use this. This is called a Celis crucible. On the bottom of the Celis crucible is a fritted glass disc. In this fritted glass disc, it has tiny pores. The tiny pores allow the water to get through, but small crystals should be trapped. The tiniest of tiny crystals probably could still get through, but those aren't even visible to the naked eye. The problem with the Celis crucible is it's very slow even without any crystals. So the first thing is I just put in some DI water in here. I put in DI water in here, and hopefully I can start seeing it get wet on the bottom, but I don't even see it getting wet on the bottom yet. This is pretty slow. And so it looks like none of this is filled with DI water now, and I'm not getting any drips down here. And so that's how non-porous that is. I mean, it's slightly porous. So what we have is a filter flask. The filter flask is Erlenmeyer with a neck. The neck is so you can attach a rubber tube. This is vacuum tubing. Vacuum tubing is thick-walled so it doesn't collapse under vacuum. And then we have a vacuum tap in here, the yellow tap. Do you hear that vacuum? And so you could test that vacuum here. It's not too powerful, but you know, your hand will get stuck on it. And so we want a decent vacuum there. Okay, then what we're going to do is we have a rubber gasket that we're going to use. And so I'm going to put that rubber gasket here. I'm going to make sure it's a tight seal here so that there's no vacuum leaks around the cone part of the stopper. Okay, and then I'm going to put my crucible on here, and let's see if this is now powerful enough to suck the water through. Now, do you see the water dripping there? We need the vacuum assistance to suck the water through. And so what we're doing is we're creating low pressure here. We have atmospheric pressure out here pushing down. So the atmospheric pressure is just pushing the water through here. How much does the atmosphere weigh? I mean in pounds per square inch. 14.7. 14.70 pounds per square inch. So you want a decent vacuum here. I got a good vacuum. You hear that? That's a pretty good vacuum. Okay, now the thing is we do not want to stir. what you want to do is you want to pass most of the liquid through here as possible. And then at the very end, okay, this is easy to knock over, so we got to be careful. So what some people do is they'll put a clamp here to prevent it from being knocked over. And so there are two ways you can clamp it. You can clamp it with a utility clamp like this, and just loosen the wing nut here or tighten the wing nut. I like to squeeze this so I can tighten it or loosen it rapidly, and then just squeeze this and then just tighten this, the right. This is just so you don't knock it over. One of the things you do in lab is you try to keep the countertops clean, because in case you do knock it over, hopefully the countertops aren't so dirty it's going to contaminate it. So you try to recover it off the countertop. It's happened before. Okay, so I have this set up here like this. Okay, so what you need to do is you need to pass as much liquid through here as possible, because that's going to go fast. And then when you're down here, you have very little liquid left, you'll stir this up and then pour in the slurry. The problem is once you pour in the slurry, it's going to slow things down, because the filter is going to get clogged, basically, and it's going to take more time. So wait until the very end. Now, you're not going to be able to get all the barium sulfate out of here by pouring it. And so what you do is you do this. Actually, let me show you the pouring technique first. I'll just do this with tap water to save money here. We have a fixed budget for DI water, and some semesters we run out of money. And we have to... So they have a emergency supply of DI water there. When you pour the liquid out, we use a stir rod. Water loves glass. Oops, I spilled some out here. You don't want to do that, so what I'm going to do is shorten this. You don't want to touch this either, but you use a stir rod to provide a surface for this to drain down. And since water loves glass, that's why it forms a concave meniscus. We can do it like this, so you can do it. Just be careful, because I'm spilling a lot on the outside. You don't want to do that. You want to be a little more careful. And so you might want to test this beforehand. Maybe this stir rod's dirty. It seems to be working okay. Water also loves itself, so that's why it sticks together. Okay, then at the very end, pour the slurry in, and then what we do is we wash any residual crystals in there. And so to wash the residual crystals, this has a little neck pouring spout here, so you might not even have to use a stir rod, because this pours nicely through the mouth. But the thing is, the angle, it might be too much to get the to prevent the precipitate from going over. But the remaining precipitate, we wash off the walls here, and then pour it in here. Wash it off the walls and pour it in. Okay, you don't want to wash with too much, because even though barium sulfate is insoluble, a little bit does dissolve. So if you keep washing and keep washing, you're going to dissolve a little bit, dissolve a little bit. Does that make sense? But then you don't want to use too little either, because you might lose some crystals there. And the other thing is, we want to make sure we wash this thoroughly. What are we going to wash with? Are we going to wash with DI water, or are we going to wash with hydrochloric acid? So did anybody skim through the procedure? At some schools, they really don't give you much time, and since some students are pretty gung-ho about this stuff, pretty determined, they really don't give much instruction sometimes either. Like I remember some labs, they just the teaching assistant would come in and say, "Any questions?" This is after the quiz. Any questions? No questions? Okay, get started. That's it. No discussion. You come in, you have to figure everything out. And if you don't figure everything out, that you can ask questions, of course. But be prepared for that, and then you'll be fine. You know, a lot of people will complain initially and then get used to it. I don't remember. Does somebody have it?
200 milliliters of hot DI water with 10 drops of 6M hydrochloric acid, right?
Yeah. So what we're going to have to do is we're going to have to make some hot water. 200 milliliters. You don't have to use a grad cylinder. Just find, or you can if you want. If you have a beaker that shows 200, this is good to plus or minus 10%. We'll just fill this up to 200 milliliters. And then 6 drops, 6M hydrochloric, throw it on the hot plate. And then this is what we're going to use for a wash solution. Because this is like, you know, the barium sulfate is like stepping out of the ocean. It's going to be salty on the outside. We've got to make sure we wash all that salt off. Is that clear? Okay, usually what I do is after I get the 200 you could leave it in the beaker, but sometimes I just pour it into a wash bottle and then just spray it. Speed things up. 200 m's enough, more than enough, because we aren't going to wash it with that much. So you probably can end up sharing it with others. All right, once we've thoroughly washed it, so that there's no more what we call, you know, this CCS above here, we have a precipitate, and the CCS we call supernatant solution or decantate. Once there's no more supernatant solution contaminating our crystals have been thoroughly washed, then what we do is we remove the crucible. So we'll turn off the vacuum and then break this here and remove the crucible. But the problem is this. Now I want to recover the precipitate, and well, first I got to dry it because now it's going to be contaminated with HCl. But if we dry it in the oven, and HCl is a gas, eventually it will evaporate out. I can't get it out of here easily because some of the tiny crystals are trapped in the fritted glass. And so what we do with these is we do this. Before I do the filtration, the first thing I'm going to do is I'm going to weigh these dry. These have been drying in the oven here, and there could be surface, you know, water loves glass, water loves ceramic, and so there's going to be surface contamination with water, so we dry it. And then you're going to have 3 of these, like this. So we're going to take these and then out of the oven, and then we're going to put these into a what to cool down? Into a desiccator to cool down. Once they're cool enough, then we're going to weigh these on the balance. But are you going to touch these with your fingers? No, don't touch these with your fingers. Use a Chem wipe or paper towel and weigh these. Once you weigh them, can you touch them with your fingers? Yes, you can, because we're going to wash them anyway afterwards. So after you weigh it, then go ahead and handle it with your fingers. If there's fingerprints on there, you can wipe them off later. But you're going to get lots of fingerprints from setting up this apparatus anyway. So we'll wipe them off when we do it. Okay, so once I collected all my samples, then you're going to put all 3 samples into a beaker, hopefully your numbered beaker like this, cover it with a ribbed watch glass, and place it in the oven over there. And then we're going to crank up the oven, and then we're going to dry these over a couple of nights, over the weekend. So by the time we come back next week, we should have, you know, freshly clean, dry barium sulfate precipitate. And the hydrochloric acid will evaporate off easily. All right, any questions? Okay, so you're going to have to get crucibles desiccator, but first crank up your hot plate so you can make some hot water for the washing.